tests for convergence. There are many tests to determine if an infinite series converges or diverges. We're going to start with the nth term test. This is a test for divergence only. If the limit of the nth term as n approaches infinity is not equal to 0, then the series sigma a sub n, n starting at 1, or actually any integer, positive integer, to infinity, diverges. This is the nth term test for divergence. If the limit of the nth term, symbolized a sub n, as n approaches infinity is not 0, then the series diverges. Example: sigma 2n minus 1 over 100n plus 40, and starting somewhere, usually 1, and going to infinity. This series, which is 1 over 140 plus 3 over 240 plus 5 over 340, etc. In this example, the limit of the nth term as n approaches infinity is the limit of 2n minus 1 over 100n plus 40 as n approaches infinity, because the nth term refers to this. So in this example, the limit of the nth term as n approaches infinity is the same as the limit of 2 minus 1 over n over 100 plus 40 over n. The limit of this as n approaches infinity is 2/100ths, which is not 0. Conclusion: when the limit of the nth term as n approaches infinity is anything other than 0, we say the series diverges. When I say the series, I'm talking about this or this. Another example: sigma 1 over n, n starting at 1 and going to infinity, which is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus, and so on. This series can be grouped as follows: 1 plus a half plus, now I'm going to group these two like this, 1/3 plus 1/4 plus, I'm going to group the next 4, 1/5 plus 1/6 plus 1/7 plus 1/8 plus, now I'm going to group the next 8, 1/9 plus 1/10 plus up to 1/16 plus, and I'm going to group the next 32 terms, 1 over 17. Actually, I meant to say the next 16 terms, 1/17 plus 1/18, etc., up to 1 over 32 plus, this goes forever. What we see by doing this is that, well, these two add up to more than 2 times a fourth. Let me erase this equal sign. This sum here, which goes to infinity, is more than one plus a half. The two terms here, a third plus a fourth, is more than 2 times a fourth, because a third is more than a fourth. These 4 terms here, these 4, would be more than 4 times 1/8, because each of these fractions up to the 1/8, each of them is more than 1/8. These 8 terms in here, in this set of parentheses, is more than 8 times 1/16, because each of the fractions is before the 1/16 is more than 1/16. The fractions in this set of parentheses, there are 16 of them, and the total of those numbers is more than 16 times 1 over 32, because each fraction before the 1 over 32 is more than 1 over 32, and so on. This series, sigma 1 over n going from 1 to infinity, is more, the total of all these is more than what I have right here. 1 plus a half, plus this right here is also a half, plus 4 times 1/8, that's also a half. 8 times 1/16, that's also a half. This 16 times 1 over 32 is also a half. And you can continue this forever. This total here is going to be infinity. We keep adding 1 plus a half plus a half plus a half forever. That will be infinity. And the total of these is more than that, more than infinity. So that means this series diverges. And this is a famous series. It's called the harmonic series. It diverges. And we want to point out that, I want to say this once again, this series diverges even though the limit of its nth term as n approaches infinity, the nth term is 1 over n, even though the limit of the nth term as n approaches infinity is 0. So the moral of the story is, when the limit of the nth term as n approaches infinity is not 0, conclusion, series diverges. When the limit of the nth term as n approaches infinity is 0, we might still have diverging, like right here. So we say that with this information alone, no conclusion can be made. The series might diverge, like the harmonic series, and it might converge. So another test for convergence or divergence is called the integral test. And this is the integral test. Sigma a sub n, n going from 1 to infinity, converges if and only if the integral of f of x dx from 1 to infinity converges. Where this is a function of x, but if we made it a function of n, the same function, it would equal the nth term of the series. And the function that we're integrating here has to be continuous, positive, and decreasing. An example is the harmonic series. Sigma a sub n, n going from 1 to infinity. I meant to say sigma 1 over n. This series, which is 1 over 1 plus 1 over 2 plus 1 over 3, etc. It's called the harmonic series. We already know that it diverges. We know that, we just saw that example. But we could prove it a different way. Change the sigma to an integral. Change 1 over n to 1 over x. Don't forget the dx. And 1 to infinity gets attached here. This is called an improper integral. There's a whole video on improper integrals. So you remember that to evaluate this integral, we replace the infinity with something like a. Infinity is gone, a is in its place, and this goes in front. The limit as a approaches infinity. The integral of 1 over x dx is the natural log of the absolute value of x. I'm leaving out the absolute value because I know the x values are all positive. It starts at 1 and goes to infinity. No absolute value necessary. And instead of plus c, we put a bracket with these attachments, which means the natural log of a goes in place of x minus the natural log of 1. And we need the limit of what we have there as a approaches infinity. A is approaching infinity, and the natural log of infinity is infinity. Natural log of 1 is 0. Infinity minus 0 is infinity. When we get this, for our improper integral, when we get this, we say the improper integral diverges. When I say the improper integral, I'm talking about the integral of 1 over x dx from 1 to infinity. And the series sigma 1 over n, n going from 1 to infinity. The integral test says that both of these do the same thing. Either the improper integral and the series matching both converge or they both diverge. In this case, they both must diverge. I'm going to do two more examples of the integral test. Sigma n over n squared plus 1, n going from 1 to infinity. To apply the integral test, we first note on a calculator, possibly, that the function x over x squared plus 1 is continuous, positive. For these x values from 1 to infinity, this will always be positive, and it has to be a decreasing function. You would only apply the integral test if this function is all three of these things. So check out the graph of this function, and you'll see that it's all of these. Sigma becomes integral, n's become x's. Integral without a dx doesn't make sense, and 1 to infinity. To do this integration, we're going to let u equal x squared plus 1. The derivative of u would be 2x dx, which means the 2 needs to appear here. Abracadabra. But don't forget the 1/2. That's 1/2 the integral of du over u, which is 1/2 the natural log of u. That's actually 1/2 the natural log of x squared plus 1. Note, x squared plus 1 is always positive. That's why we don't need the absolute value. Plus c is not used. Instead, we have a bracket with an a and a 1. The a is taken the place of infinity. Putting a in place of x, 1/2 the natural log of a squared plus 1, minus, and now putting the 1 in place of x. 1 squared plus 1 is 2. And don't forget, improper integral means since a replaced infinity, you need in front of this the limit as a approaches infinity. And if you square infinity and add 1 and then take the natural log of that and then take half of that, you'll still get infinity. And then take away some number that's still infinity. So the improper integral, and the series both diverge because of this result right here. Okay, one more example of the integral test. Sigma n over n squared plus 1. N starting at 1 going to infinity. The function x over x squared plus 1 is continuous, positive for these x values from 1 to infinity, and it's decreasing. Make a note of that in your mind. Change sigma to integral. Make all the n's x's. Dx, 1 to infinity. We're going to let actually this is the example we just did, so let's start over. This is the one, sigma n over e to the n, and 1 to infinity. Change the sigma to integral. Make all the n's x's. Don't forget the dx, 1 to infinity, 1 to infinity. We now have an improper integral. Two things here, an infinite series and an improper integral. The integral test says both of these things either diverge or they both converge. We're going to make this the limit as a approaches infinity of the integral of e to the negative x negative x times x dx from 1 to a. We get to practice integration by parts here. We're going to let u equal x and dv equal e to the negative x dx. If u equals x, then du equals dx. And if dv equals e to the negative x dx, then d equals negative e to the negative x. We now have the integral of u dv, because this is u and this is dv. Over here. The integral of u dv is always uv minus the integral of v du. In this case, u is x, v is negative e to the negative x. Copy the minus, copy the integral. V is negative e to the negative x, and du is dx. Put all the information for these up there. This is now negative x e to the negative x. Two negatives here, so that's plus the integral of e to the negative x dx. That's negative x e to the negative x. And the integral of e to the negative x dx is negative e to the negative x. Instead of plus c, we're going to put a bracket with the a and the 1. All the x's get replaced with a's. Negative a e to the negative a minus e to the negative a minus. Now all the x's get replaced with 1's. It's negative 1 e to the negative 1 minus e to the negative 1. And don't forget this a was actually taking the place of infinity, so we need in front of this the limit of all that as a approaches infinity. Bring down the limit as a approaches infinity. This is negative. This term is negative a over e to the positive a. This term is negative 1 over e to the a. Minus minus here becomes plus 1 over e. Another minus and a minus becomes plus 1 over e. Some of these fractions can be combined because they have the same denominator. The limit as a approaches infinity. Negative a minus 1 all over this common denominator, e to the a, plus 1 over e plus 1 over e, that's 2 over e. A couple reminders about limits. When we have the limit of a sum here, we can write the sum of two limits. In other words, the limit can be distributed. I'm going to write the limit of this first term, negative a minus 1 over e to the a, plus, and then another limit for this second term. Both of these are a approaching infinity. Now, another thing about limits is if there's a constant multiple, like this negative 1, we can put it to the left of the limit symbol. So this now becomes a plus 1 over e to the a, because negative 1 times a plus 1 is this numerator. And more about limits. The limit of a constant is the constant. It does not matter what a is approaching. There's no a over here. This limit can be accomplished using L'Hopital's rule, because if a is infinity, the top and bottom of this are both infinity. We can use L'Hopital's rule for infinity over infinity. And one gets brought down. L'Hopital's rule. We replace a plus 1 with its derivative with respect to a. That's this variable. We replace e to the a with its derivative. The derivative of e to the a is e to the a. bring that down. And as a gets larger and larger and larger and larger, e to the a will get larger and larger, and 1 over that will become 0. So this says -1 times 0 plus 2 over e. And because the improper integral way back here, improper integral is equal to something other than infinity, the improper integral and we just show that that is equal to 2 over e, which means this improper integral converges. So this series, sigma n over e to the n, and going to infinity, both of these things converge. By the integral test.